Previously, we showed that the ALDIC can track the DIC deformation, and we showed for the uniform Q4 mesh. So however, in the real experiments, the geometry can be more complex. So for example, here, we have the sample and there's the hole in the center. So how do we deal with this like non-uniform geometry? So here I introduce how we use the quad tree adaptive mesh to solve these problems. And particularly for the adaptive quad tree mesh is quite robust and flexible to approximate arbitrary like non-uniform and complex geometry. So basically here you can see near the hole in the center, so the mesh will be depthly refined and each of those subset or element, they're still like a square shape. And if you choose the size for the element to be a power of 2, you can see all the nodal points, you can put them into the integer pixel on the images. So you don't need to interpolate like for the subpixel, particularly for those accuracy for the grayscale value for those nodal points. So this can be used to reduce the interpolation error for those mesh. And also for the quad tree mesh, it's quite efficient. So in the LDIC code, so you can go to our app web page, download the newest version. So once you download this and unzip, you can go to the folder. So basically, I will show you some results. For example, how do we provide this solution? This is sample 12 from the DIC challenge problem. We solved the displacement U and the V and the string field EX, Y, UYY. And also we computed the shear principal strain, and we also computed the stress. So for example, here the stress. So I will do the demo for how to use this code here. So basically, I just delete these images. So this image is from the sample 12 image. It's a uniaxial tension experiment based on a hole. So for the save the time, I just do 2 frames here. So you can see it's uniaxial tension. So all the code is quite straightforward. So following the ALDIC code. So, but you just open the new code called mean ALDIC quad tree. All this code structure and lots of functions are the same at the previous meanaldic.com. So here I still just run them section by section, but once you are familiar with the code, you could just run them once. Or once you are doing the image sequence, you can also run them once, and the for loop will be will run just automatically. So I will run the first section. Just one comment is when you run the first section, you need to know you should be in this subfolder with the ALDIC. Sometimes you may have this error because it's already have the max had been set up. So once this happens, you can just change the max line to be the try this line and then catch and to ignore this line. But just pay attention is you need to stay on this subfolder. Otherwise, it cannot find this BA interp to CPP file. So once we run this line, again, you will see the very nice solution on it. Okay, so we have those max set up successfully. And after that, we can run the section 2 to load the image. So here you just double check this image folder is already added to the path. So here is already added. And I wrote this section. You can just manually search the select the images, or you could just select the image folder. So here, just select the image folder. It's this folder. And then I define the region of interest. Basically, I click the top left corner point and then the bottom right corner point. And for the steps size, I can use the large even number or like a medium even number. So usually I would recommend this to be a little bit like not that small. For example, here I use 40. And for the step, because we want to do the adaptive quadratic mesh, so this neighboring distance, so the distance between neighboring subsets needed to be a power of 2. So here we just input the 32, for example. You can also try 16 or 64 pixels. And here, this desktop, I have 4 parallel ports. If you don't have the parallel computing power, you can just use a single cluster, just a little more like a slow, but it still work very well. Before I run because I will show you to do this, to do the section by section. So I just first stay in the second frame for these images. So now we are in the second frame. And also for here, I only have the 2 image in this subfolder. So that's why the total image number also just 2. Same thing, I do the initial guess for the deformation. So here, I will do the whole field search. So basically for this initial guess search zone, we will start from the small value, for example, 3, and just do the trial and error method to find the good initial search zone size. So for example, I tried 3, I found this arrow is quite like noisy. And also you can see there are lots of those deformation is already 4, it's larger than 3. So which means this initial guess size is too small. We need to further increase this size. So next time I will try 10. So are you satisfied with this initial search current search region size? I will say I'm not satisfied. So I will increase this to 10. So I do this one more time, I can find the solution much better. But however, you can see there's still some of those regions touch the like upper bound for this 10. So I need to further increase this 10. So for example, to be the 13. Sometimes if you have this box, you could just Ctrl+C, stop the subsection, and then rerun this subsection. So once you are familiar with this, you can just code this by the code. You don't need to manually input all this parameter anymore. So here I just do here I search for the 13. It's very quickly I get to the FFT searched. So now the deformation looks very nice. Not only they are smooth outside the hole, also because if you look at the magnitude for the displacement, so here around the 12 pixel, it's smaller than the 3 value, which means this search size is a good one. And also because there's the hole there, so there's bad points in the whole area. So now I'm satisfied with this initial guess, and I can set bounds to further remove the bad subsets. But however, here outside all the outside the hole, they all looks very nice. So I just don't remove any bad points now. So I just skip all these sections. You can press the 1, or you can just press the Enter key. The 1 is because if you want to do this, it's just a 0. If you want to skip, you press 1. Okay, then let's go to the next section, the section 3 star. So this section, you will generate the mesh considering those whole structure. And also you will have the image mask. So follow this rule. First, click some points along this whole boundary. At least you need to click 5 of those points. So here I just around this whole geometry, I click 5 or 6 points. And then the circle will fit by this clicked points. And after that, we need to compute the image mask. So basically here is we select some points inside the hole, and then we click some points outside the hole. And based on the image grayscale value, we can automatically find the image mask. So here I just click 7 points inside the hole. And then I click more than 3 points outside the hole. So here I click a few more of those. And this hole is darker than the sample. So sometimes the hole can be brighter than the sample. So just based on what's your experimental setup. So here I choose the darker one. And then you can see the image mask had been generated. And also previously the FFT search initial guess can be interpolated based on this adaptive mesh. And if you further to zoom in the mesh near the hole, you can see it's a very nice quad tree mesh. Yeah. And then I run the section 4 for the local step. So it's very fast. And I can also manually to remove some bad points if they are, but now it looks like very nice. So I don't remove any points anymore. So I click no, and I click no. And similarly, as the previously ALDIC code, I can run the global step. Basically, this step is to solve the kinematically compatible solution. And then also from the finite mesh, we can still get the string field. Look at here, we have the displacement UV and also other string components. So after that, we can just do the ADMM iterations. Basically, we run this local step, global step, and do them iteratively until they get convergence. So usually this convergence is super fast. It's usually within 3 to 5 steps. So you can just change this. So that here the default is the 3 or 4 iterations, but you can manually change this number to 3, 4, 5. Basically, after the third steps, there's not quite a big difference. And once they converge, you will get the solved displacement field. Yep. And now you can just plot to see the computed deformation and also the string field computed by the final element. We further to run the section 7 to remove some temporary mat file here on the left because there's some sub-steps solution. We just remove these M files. And also we can run the section 8 to compute the strain and the section 9 to compute the stress. So here I run the section 8. Do you want to smooth? I don't want. And also I compute a small strain based overlay with the current deformed configuration. I plot the use the GPG and I gave the transparency 0.5. So all these will overlay with the original images, and they will be saved in the GPG format. So here I output like all of these, like displacement and all of these string components, UIY. So if you look at the folder, you can see they all look very nice. And also all the solved solution, it is saved in the string result. So if you go to the result string, if you click the structure, you can see all the components are saved here. And also the size of each component, 2, 3, 8, 9, they also have the x coordinates, displacement u, and also string, they are there. And also, if you assume the materials have some material model, for example, linear elasticity, you can also compute the stress field. So here I assume it's a plane stress linear elasticity problem. And I assume the Young's modulus is 69, 10 times of 9, for example. And the Poisson ratio is 0.3, for example. So I can also plot the stress field. So look at the folder. You also have the stress field here. This we have some problem. Okay, finally you save all the results again. That's all. If question, just leave your question on the piazza. So once I see it, I will answer your question. And finally, have a happy Thanksgiving.